The purpose of any theory of relativity is to be able to take the experience of observers in different reference frames and relate them to one another. However, since experiences can look very different between reference frames, we need a way of changing the experience of one observer so that it matches up with the experience of another. In more mathematical terms, we need to find transformations which relate the two reference frames. Let's try to do this for observers in special relativity. We will begin as we have been, with Isaac standing on a planet as Albert flies by in a rocket ship at some velocity v. Now, we'll have Isaac and Albert measure the distance to a star which is not moving according to Isaac. Therefore, to Isaac, the star will always be the same distance away, call it delta xi. Now, as Albert moves closer to the star, he'll measure a distance which is getting shorter. Since this change in distance will just be velocity times time, Albert will measure a distance to the star, delta xa, which is equal to some initial distance minus v times the time elapsed according to him. We know that the minus sign must be there since the distance to the star is getting smaller. If Albert began his measurement as soon as he passed Isaac, then we might initially think that the initial distance is equal to delta xi. However, we have to remember that lengths will be contracted since Albert is moving relative to Isaac's and the star's reference frame. Therefore, the initial distance will be 1 over gamma times delta xi, where gamma is just the usual gamma factor. Now we can solve for delta xi to find a way of describing distances to the same object according to two different observers. But now what? How do we know that there's more to do? Well, in my last video, I showed that there's a quantity, delta s squared, that does not change between reference frames. In other words, it's an invariant. If we assume that Albert is just traveling in the x direction, then that means that nothing is different between the two reference frames in the y and z directions. So these terms will just be the same on both sides of the equation and cancel off. Now we can plug in what we found before for delta xi in terms of delta xa and delta ta, and after some tedious algebra, we find that the two sides are equal if the time elapsed in Isaac's frame is written as gamma times the time elapsed in Albert's frame plus v over c squared times delta xa. Since our invariant quantity now holds true as long as our reference frames are related by these two expressions, we have succeeded in finding the transformation between any two reference frames in special relativity. For historical reasons, this transformation is known as the inverse Lorentz transformation, and transforms the experiences in Albert's frame to experiences in Isaac's frame. To find the standard Lorentz transformation, all we have to do is realize that, according to Albert, Isaac is moving at the same velocity v, but in the opposite direction. So everywhere in our transformation, we just need to replace v with minus v, and we have the Lorentz transformation, which relates experiences in Isaac's frame to Albert's frame. But hold on. We only found the expression for if Albert is traveling in a very specific direction, so don't we need to find a more general transformation if Albert is moving in a more general direction? I'm curious as to what all of you think the answer is to this question, so leave a comment with your answer and your reasoning as to why you chose it, and I'll answer it in the next video. I know this may seem like a bunch of mathematical formalities, but the Lorentz transformation is the key to special relativity. With it, we'll be able to do all of the physics we want, and in doing so, we'll find some surprising and amazing results.